Yeah, very good evening to all viewers and students. In the last session, I've covered what is the three-phase induction motor, what are the construction details, what are the types of induction motors, and what is the principle of operation of three-phase induction motor, and how the torque is produced, and what do you mean by slip, and what is speed, rotor frequency, what are the characteristics that we have studied already in the last session. So in this session, I'm going to cover introduction about three-phase induction machines, torque equation, expression for maximum torque and starting torque, torque slip characteristics, and what are the basic tests performed in the three-phase induction motor, no-load test and block rotor test. And next, speed control methods. And finally, induction generator. So in the university, the question may be asked like this: derive the equation for full load torque, maximum torque, and starting torque in an induction motor in terms of the applied voltage and motor parameters. So he is asking, derive the equation for full load torque, maximum torque, and starting torque in an induction motor in terms of applied voltage and motor parameters. Motor parameters are nothing but rotor resistance, rotor reactance, and slip. So to derive the torque equation, we know that the torque produced in the three-phase induction motor is due to interaction of stator flux as well as rotor flux, and the angle between stator flux and rotor flux, that will be cos phi 2, or the stator flux is directly proportional to induced EMF in the rotor, and rotor flux is directly proportional to current flowing in the rotor. And we know that power factor cos phi 2 is R2 by R2 square plus Sx2 whole square. And in the previous session, we have already drawn the equivalent circuit. We draw directly the rotor equivalent circuit. The slip is E2 and the induced EMF is E2, slip is S. The rotor resistance is R2 and rotor reactance is Sx2. The current flowing in the rotor circuit is I2. Right. Now, if you resubstitute here, the torque expression can be rewritten as T is equal to some constant K, phi s can be written as E2, and phi r is nothing but E2, and cos phi 2 is nothing but R2 by is the impedance. So here I2 can be written as I2 equal to SE2 by square root of R2 square plus Sx2 whole square. And from this right angle triangle, we can consider this is R2 Sx2. So this is the hypotenuse. The phase angle between R2 and Jx2 is phi 2. So from this right angle, cos phi 2 is adjacent by hypotenuse. So R2 by square root of R2 square plus Sx2 whole square. So now we can resubstitute cos phi 2 as R2 by square root of R2 square plus Sx2 whole square. So from this, we're going to get torque T equal to K into E2, and also I2 can be replaced by SE2 SE2 by square root of R2 square plus Sx2 whole square into R2 by square root of R2 square plus Sx2 whole square. So by simplifying this equation, we are going to get K into E2 into E2 square S into R2 by square root of R2 square plus Sx2 whole square into square root of R2 square Sx2 whole square. This will be T equal to K E2 square R2 into S divided by square root of R2 square plus Sx2 whole square, root into root, whole square will get R2 square plus Sx2 whole square. So this is the equation for torque. In this, starting torque can be found out. Starting torque is obtained when slip is 1. Means rotor speed is 0. What is the formula for slip? S is equal to ns minus n by ns. At the time of starting, speed of the motor is 0. So therefore, since speed is 0, then what could be the slip? S is equal to ns minus 0 by ns. So slip is 1. At the time of starting, slip is 1. So therefore, the starting torque is given by TST when slip is 1, which is equal to K into E2 square R2 by R2 square plus Sx2 whole square. Right? Then similarly, full load torque. The full load torque is obtained when the slip is at full load. So slip is at full load means SFL is equal to ns minus full load speed by ns. When the slip is substituted at full load, then the torque expression will be torque T at full load is equal to K into E2 square. In place of slip, we have to substitute full load slip. SFL into R2 square divided by R2 square plus SFL x2 whole square. This is the formula for full load torque. So students, please note down this. How to find out the starting torque? When slip is 1, when the speed of the motor is 0, slip will become 1. We resubstitute in the torque expression S is equal to 1. That could be the starting torque. At full load, the speed will be at full load speed, the slip will be SFL. If we replace in the torque equation in place of S, SFL, you are going to get the full load torque. Now you are going to derive what is maximum torque. Maximum torque. The condition for maximum torque is, we know already, we have derived the torque expression K into E2 square S R2 by R2 square plus Sx2 whole square. This is the torque equation. So what is the condition for maximum torque? Here we are going to find out maximum torque. So condition for maximum torque. What is the condition for maximum torque? So this is the torque expression. If you differentiate with respect to variable term ds and equate it to 0, you are going to get the condition for maximum value. So therefore, d by ds of the torque T, K E2 square S R2 by R2 square plus Sx2 whole square, and finally equated to 0. So if you differentiate with respect to S and equate it to 0, this is constant K, you can directly equate it to 0. So differentiate with respect to S. S is the variable here. We are consisting in the both numerator as well as denominator the S value. So how can you differentiate? By applying U by V rule. So V square R2 square plus Sx2 whole square R2 square plus Sx2 whole square into differentiation of this term. Already we have K is there, K directly we can equate it to 0. So therefore, the next variable term is differentiation of this term. So differentiation of S is 1. So simply E2 square R2 minus next term, this term into E2 square S R2 SR2 differentiation of the denominator term. So R2 square is anyway constant, differentiation of Sx2 whole square. So Sx2 whole square is nothing but two Sx2, which is equal to 0. Now equated to 0, the denominator term directly equated to 0, 0. So therefore, you can directly take down the common of E2 square into R2. So E2 square into R2 square plus Sx2 whole square minus 2 S square x2 square equal to 0. So this is constant, E2 square R2 is constant, we can equate it to 0. So therefore we have R2 square plus S square into X2 square minus 2 S square X2 equal to 0. So R2 square plus S square X2 square minus 2 S square X2. R2 square minus S square X2 square equal to 0. So this will be in the form of A square minus B square form. So R2 plus Sx2, A plus B into A minus B. R2 minus Sx2 equal to 0. So therefore, R2 equal to minus X2. The slip cannot be negative. So R2 equal to Sx2. So finally, get R2 equal to Sx2. R2 equal to Sx2. So what is the condition for maximum torque? If you differentiate and equate it to 0, we are going to get the condition for maximum torque is S is equal to R2 by X2. This is the condition for maximum torque. If we resubstitute this condition in the torque expression, then you are going to get the maximum torque value. So this is the condition for maximum torque. So substitute in the torque expression, torque T equal to K into E2 square S R2 by R2 square plus Sx2 whole square. Right, this is the torque expression. Then to get the maximum torque, T will be T max when S is equal to S max. When S is equal to S max, which is nothing but R2 by X2. So this will be equal to, in place of S you have to substitute R2 by X2. Then we are going to get the maximum torque. T max is equal to K into E2 square. In place of X substitute R2 by X2 into R2 by R2 square plus R2 square by X2 square into X2 square. So finally we are going to get K E2 square R2 into R2 R2 square. Here we can take it out, R2 square common, R2 square by X2 in the denominator. X2 square get cancelled out. So 2 times of R2 square, right? So in this, we can cancel out these two. So finally, the maximum torque will be obtained as T max is equal to K E2 square by 2x2. Whereas condition for maximum torque is at a slip R2 by X2, we are going to get the maximum torque. Here one important points you can note down is the slip at which the maximum torque occurs depends on the rotor resistance, but the maximum torque is independent of rotor resistance. and it is inversely proportional to reactance. But the slip at which the maximum torque occurs directly depends on the rotor resistance. As rotor resistance increases, slip increases. When the slip increases, ns minus n by ns, then n is equal to ns into 1 minus s. If slip increases as rotor resistance increases, but speed of the motor will decreases. Next, the next important question that was asked in the university exams is derive the relationship between full load torque and maximum torque of in a three-phase induction motor. Just now we have derived the expression for maximum torque and as well as full load torque. Just compare. The torque expression is directly we can written as K into E2 square S R2 by R2 square S X2 whole square. So in place of slip, if you substitute full load slip, then that will be the full load slip. So full load torque SFL. So TFL when slip equal to SFL. The full load torque when slip is equal to SFL, full load slip. So K into E2 square in place of S substitute SFL R2 by R2 square plus SFL whole square into X2 square. This is the full load torque. Similarly, we know that, let us assume this is equation 1. Already we know that maximum torque is given by T max is equal to, we are going to get the maximum torque at S is equal to S max. What is the condition? R2 by X2. We resubstitute in this expression, directly we have already derived just now. So what is the expression? K E2 square by 2x2. Assume this is equation 2. He is asking the ratio of full load torque to maximum torque. Just divide equation 1 with equation 2. So TFL by T max, which is equal to K into E2 square SFL R2 by R2 square SFL whole square into X2 square divided by maximum torque divided by K E2 square 2x2 divided by K E2 square. So these two will cancel out. So the remaining term is TFL by T max, which is equal to full load slip 2 R2 X2 by R2 square plus SFL square into X2 square. Now we can take here in the denominator X2 square common. By we take out x2 square common, r2 square by x2 square plus sfl whole square. These two terms will get cancelled out. So the ratio of full load torque to maximum torque is given by 2 into sfl r2 by here 1 x2 cancel out with x2. So 1 is remaining by r2 by x2 whole square plus sfl square. So this is the full load slip and this is maximum slip. So let us assume the full load slip is SFL and maximum slip is, let us assume A. A is nothing but R2 by X2. So therefore, full load torque to maximum torque ratio is given by 2ASFL by A square plus SFL whole square, where A is the slip at which the maximum torque occurs. SFL is the full load slip. So from this, we can also derive the ratio between starting torque to maximum torque also. So when it is a starting torque, then slip will be 1. Right? So when slip is 1, then that will become starting torque. So when SFL is equal to ST, starting slip, starting torque, if it is, slip will be 1. When full load slip becomes starting, when S is equal to 1, then we can find out the starting torque to maximum torque, which is given by 2A by A square plus 1, where A is R2 by X2. For starting, 2A by A square plus 1. For full load, 2A SFL by A square plus SFL whole square. Clear? Just note down. So very, very important problem. Just now we have derived the relationship between full load torque and maximum torque, starting torque and maximum torque. So a question may be asked like this. A 6-pole, 50 Hz, 3-phase slip ring induction motor has resistance and reactance of 0.5 ohm and 5 ohm per phase respectively. Calculate at what speed the torque is maximum. Second bit, the ratio of maximum torque to starting torque. What must be the external resistance per phase have so that the starting torque is of the maximum torque. Just now we have derived the relations. First of all, write down the given data. A 6-pole, 50 Hz, 3-phase slip ring induction motor. Number of poles is given 6, frequency 50 Hz, 3-phase slip ring induction motor. As resistance and reactance. These are rotor resistance and rotor reactance, 0.5 and 5 ohm. R2 is 0.5 ohm per phase and X2 5 ohm per phase. respectively. Calculate first bit, at what speed the torque is maximum. Is asking what is the speed. At what speed the torque is maximum. Right. We know that maximum torque is occurred at, what is the condition for maximum torque? Maximum torque is occurred at a slip of S max, which is nothing but R2 by X2. Right? He is asking the speed at which the maximum torque occurs. Generally, maximum torque is occurred at this condition, at a slip of R2 by X2. That is maximum slip. So, what is the slip at maximum torque condition? S max is equal to R2. What is R2? R2 is given as 0.5 and X2 is given as 5. So, slip will be 0.1. So, slip as it is a ratio, it won't have any units. So, what is the formula for speed here? Speed at the maximum torque. So, generally what is the expression for motor speed? In terms of synchronous speed, ns into 1 minus s. And here we are finding for speed at the maximum torque. Maximum torque is occurred at a slip of S max. So, this will be S max. Then what is ns? From the given data we can calculate ns. Synchronous speed formula 120 F by P. Number of poles P6, frequency F is 50 Hz. So 120 into 50 by into 50. So 1000 RPM. Revolutions per minute. Right? Now substitute here. NS is 1000 RPM into 1 minus slip is 0.1. So 1 minus 0.1, 1000 into 0.9. So 900 RPM. So the speed of the machine at maximum torque condition is 900 RPM. Next, go for second bit. The ratio of maximum torque to starting torque. Already we have derived the ratio of starting torque to maximum torque is 2a by a square plus 1. But he is asking the ratio of maximum torque to starting torque. Second bit. Maximum torque to starting torque. So what is the formula? A square plus 1 by 2a. Just check the formula. Starting torque to maximum is 2a by a square plus 1. T max by T starting is a square plus 1 by 2a. Right? Where a is R2 by X2. This is the condition for maximum torque. Already R2 is given as 0.5 and rotor reactance is 5. 0.1. Right, substitute here 0.1 whole square plus 1 by 2 into 0.1. So 1.01 divided by 0.2 comes what is the value? Just check it and tell me. 5.05. Right? Next. The third bit, what must be the external resistance for phase have so that the starting torque is of the maximum torque? What must be the external resistance for phase have so that the starting torque is of the maximum torque? Right. Is asking what must be the external resistance for phase to be added such that the starting torque is of the maximum torque. Starting torque is of the maximum torque. What must be the external resistance? We know that already the ratio of starting torque to maximum torque. Is the starting torque to maximum torque ratio a square plus 1 into 2a, where a is R2 by x2, a is R2 by x2, 0.5 by 5. But this is given as the ratio TST to Tmax is 1 by 2. So 1 by 2. So cross multiply, 4a is equal to a square plus 1. So simplify, you are going to get a square minus 4a plus 1 equal to 0. This is a quadratic expression. Solve for a equal to minus b plus or minus square root of b square. 4 square is 16 minus 4ac by 2a. So 16 minus 4 is nothing but 12, root 12, 4 plus root 12 by 2. So root 12 can be rewritten as 4 plus is plus or minus root 12. 4 into 3, that is 2 root 3 by 2. So 2 plus or minus root 3. We know the root 3 value is 1.732 or 2 minus 1.732. So whichever is smaller, that value can be taken here. Right? So therefore, A is equal to, what is the value? 2 minus 1.732. 8, 6, 6, 2, 2.0 minus 1.732, so 0.268. Here A is 0.268, but the question is, what must be the external resistance per phase have so that the starting torque is of the maximum torque? External resistance is asking, but actual resistance is 0.5. So what amount of resistance to be added here such that the starting torque will be equal to half of the maximum torque? So if A is equal to 0.268, we are going to get this value. So for this, (0.268), but A is nothing but R2 by X2, but here our condition is starting torque is half the maximum torque. What could be the external resistance to be added? Let us assume the external resistance is smaller such that this condition occurs. So R2 plus R by X2 equal to 0.268. Now what is R2? 0.5 plus R by capital X2, 5. Solve for R. What is the value of R we are going to get? Solve 0.84 ohm per phase. So this amount of resistance to be added externally such that the starting torque will be equal to half of the maximum torque. So one more important question is, draw and explain the torque slip characteristics of three-phase induction motor. We know already the torque expression of induction motor. K E2 square S R2 by R2 square S X2 whole square. Right? So torque slip characteristics is asking. So to draw the torque slip characteristics, let us assume when the slip is small. Naturally slip is less than 1. So let us assume when the slip is small, Sx2 is small and Sx2 whole square is very, very small compared to R2 square. Compared to R2 square. So when the slip is very, very small, Sx2 whole square is very, very small compared to R2 square. So therefore, the torque expression is given by, so we can neglect the term Sx2 whole square compared to R2 square. Sx2 square is very, very small, too low, so we can neglect this term. So this term can be neglected such that K E2 square K E2 square S R2 by, if Sx2 is whole square is neglected, the remaining term is R2 square. So therefore, the torque is given by K E2 square S by R2. So from this, torque is directly proportional to slip. When S is small, the torque is directly proportional to slip for lower values of slip. Lower values of slip. For lower values of slip, torque is directly proportional to slip. This is the first case. Next, go for second case. When slip is maximum. When slip is more, Sx2 is much more and Sx2 whole square will be much, much more compared to R2 square. If Sx2 whole square is more compared to R2 square, so we can neglect R2 square. So therefore, the torque will be K E2 square S R2 by S square X2 square. Here we are neglecting R2 square. For case 2, for case 1, we are neglecting Sx2 whole square. Now, S will cancel out. So therefore, the torque is directly proportional to or inversely proportional to 1 by S. For the first case, for lower values of slip, torque is directly proportional to S. For second case, when slip is high, for higher values of slip, the torque is inversely proportional to slip. So based upon these two cases, we can draw the characteristics. The first case is for lower values of slip, torque is directly proportional to slip. For higher values of slip, torque is inversely proportional to slip. So now draw the characteristics taking x-axis as slip and y-axis as torque. We know that slip is nothing but ns minus n by ns. Relative speed between synchronous speed and motor speed to the synchronous speed. When slip is 0, then what is the speed? Slip is 0, ns minus n by ns. 0, that implies n equal to ns. So in the first case, we have assumed for lower values of slip. Let us assume this is slip is 0, 0.5, and s is equal to 1, and this is s is equal to 2. And this side, s is equal to minus 1. Right. So according to the first case, for lower values of slip, torque is directly proportional to s. So lower values means 0 to 0.5. The slip will be directly related. So torque is directly proportional to slip. If s is low, torque is directly proportional to slip. Right. So how to draw the characteristics? So directly related means it's a linear curve for lower values. Then for the second case, what happens? For higher values of slip, that is assume 0.5 to 1. If s is high, torque is inversely proportional to slip. So torque decreases. And the maximum torque will be occurring at the maximum slip, S max, which is nothing but R2 by X2. Right. When slip is 0, the speed of the motor is ns. When slip is 1, what is the motor speed? If s is 1, When slip is 1, the motor speed will be 1 minus 1, 0. The motor speed is 0. So here n equal to 0. When slip is 2, n is equal to ns into 1 minus 2. So minus ns. N equal to minus ns. So whenever the motor speed is reversing, this condition is called as braking. This region is called as braking region. Reversing of supply terminals. So whenever the stator terminals are reversed, means the supply is reversed, the rotating magnetic flux will be reversed such that the motor speed will be reversed. So this condition is called as braking. And from 0 to 1, it is called as motoring operation. Right. So when slip is becoming negative, so at this condition, s is equal to minus 1, what could be the speed? Motor speed n is equal to ns into 1 minus s. Ns 1 minus of minus 1 plus 1. So double the synchronous speed. Motor speed will be double the synchronous speed. So this condition is called as generating. This condition is called as generating. So induction motor will act as a generator when the speed of the motor is greater than the synchronous speed. Here the speed is greater than the synchronous speed. So therefore in this region it will act as induction generator. It will act as induction generator or generator simply. So during this interval, it will act as generating. Right? So during the region 0 to 1, the induction motor will act as motoring operation. When the slip is greater than 1, 1 to 2 will act as braking operation. Then 0 to minus 1, it will act as generating. So you may expect the question, draw the torque slip characteristics and explain the regions operation of induction motor. Means regions means 0 to 1. When the slip is 0 to 1, it is acting as motor. 1 to 2, it will be acting as braking. And 0 to minus 1, the induction motor will act as generator. Right. You can observe the clear picture about torque slip characteristics of three-phase induction motor. When the supply is given, the motor is running in the forward direction. See here, the direction of ns is nothing but rotating magnetic field, and the supply is given here to the stator terminals. Three-phase AC supply is given here. RMF is produced in the stator. RMF is revolving with synchronous speed, and in order to maintain the relative speed, the rotor has to rotate in the same direction of the RMF. So rotor is start rotating in the same direction. Then as the torque developed will be also directly proportional to the speed, so torque is also in the same direction for motoring operation. If you see for generating operation, see here, for generating, RMF is produced in this direction, even though the rotor speed is in the same, but the torque produced will be in the reverse direction. some mechanical source is acting here to oppose the relative speed between ns and n. So whenever the relative speed ns minus n becomes negative, like this, when the slip becoming negative, then we are going to get this condition. So torque will opposes, as whenever the torque is moving in the opposite direction, EMF will be induced in the stator conductors. That's why this will act as a generator. So these are the various characteristics for different values of rotor resistance, how the torque slip characteristics are varying. This is for first resistance R1, rotor resistance. This is the torque obtained. If we increase the rotor resistance, the torque will rises here. Similarly, for different values of rotor resistance, we can draw the characteristics, and in each, if you observe, the condition for maximum torque is R2 by X2. Slip at which the maximum torque occurs depends upon R2. So for different values of R2, the slip will be different. This is the slip. So at different rotor resistances, the maximum torque is same, but slip at which it is occurred is different. This is S1, S2, S3, S4, like this. For different rotor resistances, the slip will be different, but the maximum torque will be same, as maximum torque is independent of rotor resistance. T max is K E2 square by 2x2. It is independent of rotor resistance. So maximum torque is always constant. Explain no load and block rotor test. The university, the important question this was asked, explain no load and block rotor test. Or the same question may be asked, what are the different tests to be conducted on the three-phase induction motor? Generally, what is the main aim to conduct the test is to analyze or to enhance the performance of the machine. So for that, you have to draw the performance characteristics, torque, speed, slip, torque versus slip, torque versus speed, and what are the losses in the machine under heating condition, under running condition, and what are the losses occurred, and what is the efficiency. So mainly for three-phase induction motor, mainly the tests performed are three types. The first test is brake test. Second one is no load. Third one is block rotor or lock rotor. Rotor is locked. So brake test can be performed in squirrel cage induction motor. As we all know, the induction motors are two types, squirrel cage induction motor and slip ring induction motor. These two tests are performed on slip ring induction motor. Now this is the circuit diagram for brake test. In our laboratory we can conduct this test. See here, these are the three-phase supply we are giving by means of a three-phase variac. This is R, Y, B. While performing brake test, to note down the voltage, how much voltage we are giving, we are connecting one voltmeter, 0 to 600 volts, and one ammeter here to measure what is the current flow in this stator. So, and here there are 2 meters to measure the power. This meter is called as watt meter, and we are connecting one more watt meter here. These 2 are short circuited, MLCV. So it's directly given to the stator winding. This is the stator winding. Which is delta connected, and this is the rotor of the induction motor. And to this, with the help of belts, in order to apply some loads, we are connecting some weights here. To tighten the belt, some weights will be applied on this rotor such that rotor speed will reduces. This is called as mechanical loading. So in this test, just under no load condition, we are giving 3-phase AC supply with rated voltage and measuring what is the input voltage, what is the current drawn by the machine, and what are the W1 and W2 readings. This W1 and W2 under no load condition gives the core losses. So whenever it is loaded with certain weights, that is indicated by S1 and S2, those difference can be measured, and by applying certain weights, the torque of the machine and the speed can be noted down. The speed of the rotor is noted down by using tachometer. So under no load condition, we are going to get what is VL, what is the voltage and current. Then under braking condition, when we are applying the brakes, certain weights are applied on this. So S1, S2 are noted, and correspondingly speed of the machine is noted, and current drawn from the supply increases as the load on the machine increases. In the same manner, respectively, W1 and W2 values are also noted down. So the input power obtained will be given by the sum of the watt meters W1 and W2. And how to find out the output? Output is nothing but we are loading the machine. So therefore 2 pi nt by 60, where n is the speed of the rotor and torque T is WRG, where W is the difference of weights S1 and S2, the difference of S1 and S2, and R is the radius of the pulley. Generally it is taken as 0.12 in the laboratory, and G value is 9.81. So by substituting torque value WRG, we are going to get output power, and input power is sum of the watt meters. Then the efficiency can be calculated by output by input. Percentage of efficiency is into 100. So in this way, we can find out the performance of the 3-phase induction motor by conducting this brake test. Next text is no load test on 3-phase induction motor. No load and block rotor test, both are conducted at a time. This is the no load test. So under no load condition, we are not at all applying any loads here. Simply we are giving rated voltage here by means of a variac, 3-phase variac. We are applying the 3-phase supply, and with the rated voltage of 415, such that the powers in the watt meters W1 and W2 is noted, and in each phase the currents drawn by the motor is noted. So here the sum of the wattmeter readings gives the no load power. The no load power is W naught, which is given by root 3 no load voltage into current into power factor. And by conducting this no load test, we are going to find out the no load parameters. What are the no load parameter? By drawing the equivalent circuit for the stator parameters, as we have seen for transformer, it is similar to that of transformer under no load test. No load means we are not at all applying any load. No load means load is 0. So RL is 0. So no load is 0, RL equal to 0. So stator resistance is R1, reactance is X1. R0, X0 is the no load current, and we are applying 3-phase voltage here, and current drawn is no load I1. So just right. So here, by conducting this test, we are going to find out R0 and X0. The current flowing through this is the I0. The current flowing through R0 is IW, watt-full component. Current flowing through reactance is magnetizing component. So from this equation, we are going to find out the no load power factor. Then after getting no load power factor, find out I0, IW and X0. And already we know what is the current drawn by the motor and what is the applied voltage. V0 from the readings, I0 from the readings, W0 is also from the readings, that is nothing but W1 plus W2. So we can calculate cos phi naught. So therefore cos phi naught is equal to W0 by root 3 V0 I0. Right? This is cos phi naught. Then find out watt full component IW is nothing but I0 cos phi naught, and magnetizing component of current I mu is equal to I0 sin phi naught. So from this, you can find out R0, where R0 is equal to, if EF is the applied voltage, you can also take it as V0. V0 by IW is nothing but R0, and X0 is nothing but V0 by I mu. So in this way, we can find out the no load parameters and no load power factor. Then go for blocked or lock rotor test. So in this test, we are using squirrel cage in slip ring induction motor. The rotor is blocked with the help of 3-phase resistive load here. So this is the rotor is blocked, and this is the stator. We are giving 3-phase supply, and rotor is blocked by connecting 3 star connected resistors like this. By means of a slip rings, we are going to block the rotor. And same way, after blocking the rotor, whenever the rotor is blocked, means the speed of the machine is 0. When the speed is 0, this is called a standstill condition. S is 1, but RL is equal to R2 square into 1 by S minus 1. Under blocked rotor test, when the slip is 1, under standstill condition, yeah. So at standstill condition, when the rotor is blocked, slip will be 1. So RL equal to R2 square into 1 by S minus 1. So when slip is 1, R2 square is 1 by 1 minus 1. So 1 minus 1 is 0. RL is 0. So by conducting this test, we are going to find out what are the total losses, copper loss, in the machine, and rated voltage, applied rated voltage, current, and what is the power factor. So WSC is equal to root 3 VSC ISC cos phi SC. So we know the applied voltage is rated voltage and the rated current noted by the ammeter whenever the rotor is blocked, and we have to apply the voltage such that the current in the meter reads to rated value, that is the rated short circuit current. So from this we can find out the short circuit power factor, cos phi SC equal to WSC by root 3 VSC into ISC. So after getting cos phi SC, next we know that VSC and ISC. What is the relationship between VSC and ISC? So VSC equal to ISC into ZS, impedance. So we can also find out the impedance, and also for 3-phase the copper losses will be 3 ISC square or 0.1, which is equal to WSC. So from this we can find out R01 WSC by 3 ISC whole square. You can find out R01, and we know that this ZSC or Z01, we can also write Z01. So from this we can find out Z01, and from this R01, and finally we can find out X01, which is equal to square root of Z01 whole square right here, X01. So we can write here X01 is equal to square root of Z01 whole square minus R01. So okay, leave it. Right. So in this way we can find out no load parameters from no load test, and block rotor test we are going to find out what is the full load power factor and what is R01 and X01. And by conducting no load and block rotor test, then what is the purpose of this no load and block rotor test? So one more advanced method to find out the performance and find out the copper losses and core losses and slip and power factor, you can go for circle diagram, which is very important. Circle diagram. How to construct the circle diagram? The data required to draw the circle diagram is no load test data, no load test data, and second one is block rotor test data. From no load test data, we can calculate, we can find V0, I0, and what is the core losses, and R0, X0, cos phi naught, what is the input current, what is the current represented in the stator winding. Actually, this is the current in the rotor which is referred in the stator I2 dash, which is acting counteract to the stator current and no load currents. These are the parameters we are going to get from the no load test data. From block rotor test or lock rotor test, what are the parameters we are going to get? VSC, ISC, WSC, and R01. It is the reactance referred to stator side, which is combination of rotor resistance and stator resistance. Similarly, X01, X1 plus X2 by K square. Right? So, and also we can find out cos pi SC, power factor angle. So based upon this data, we are going to draw the circle diagram. So let us consider voltage is taken along y-axis and current on x-axis. Now from no load test data, we can find out what is I0. I0 is the angle between V0 and I0 based upon this power factor cos pi naught. Already we have calculated here from no load test. Cos pi naught is double naught by root 3 V0 into I0. So we can find out cos phi naught here. Right. So let us represent no load current I0, which is making an angle of phi naught. Let us assume this point is A. Then find out I1. I1 is nothing but see the equivalent circuit. I1 is nothing but I0 plus I2 dash. So I1 is nothing but I2 dash plus I0. So this is the phasor term we have to consider. So I1 is phasor sum of I2 dash and I0. So first of all we have to draw for, already we have drawn I0, then draw for I2 dash, then the resultant current will be I1. Right. So if this is A, then draw for I2 dash the angle made with respect to V is, let us assume phi 2 dash, and resultant of I2 dash and I naught is nothing but I1. So just draw the parallelogram parallel to I naught and parallel to this. Now this will be I1. Already we have considered this point is A here. Let us consider this point is P, right? Now, let us draw a line parallel to x-axis. From A to parallel to x-axis we have drawn a line, and also from the block rotor test there is short circuit current which is making an angle of cos phi SC. So this is the power factor. ISC is making an angle of phi SC here. So let us draw ISC, which is making an angle of phi SC with respect to voltage. This is nothing but ISC. So if this is A, let us assume this point is B. Now if we join A and B points like this, and exactly at the midpoint of AB, let us draw a perpendicular bisector here, which cuts this line at point C, taking AC as radius. Taking AC as radius, C as center, then we can draw the semicircle. Right? So we have joined A and B points and take the midpoint, draw a perpendicular line on this line, and this point is the C. AC indicates the center of the circle, taking C as center, AC as radius, draw the circle. Draw the semicircle. If you draw the complete circle, what happens? If you draw semicircle, this is for motoring operation, and other half will be for generating. So the induction machine can be acting as a motor or generator. Right. Now what you are going to find out from the circle diagram? Now we can join this point B onto this axis, and exactly midpoint if we join with this. If this is B, let us assume C, and this is D, and midpoint of BC is assumed as E, and this linking onto the AD axis is F. Let us assume this is G. So this BE indicates rotor copper loss, and this EC indicates stator copper loss. Next, this CG indicates stator core loss. And from point P, if you draw a perpendicular line here onto the x-axis, and this AB line, the line drawn between AB is called as output line, and this AE is called as torque line. So the component which is touching AB line, this is P, now it is indicated by Q, and this Q, this point is S, T, right? So P, Q, R, let us, this point is P, the line touching the AB line is called as Q, the line touching the torque line is called as R, the line touching the so this is P, Q, and this point is R, and this point is S, this is T. So P, Q, R, S, T. So each component indicates different values. Here PQ represents the output power component, and QR indicates copper loss component, RS indicates this PQ indicates output power, and QR indicates copper loss, RS indicates stator copper loss, ST, the component indicates stator core loss. Right? In this way, we can find out the stator copper loss and rotor copper loss. Then what is the maximum torque, and maximum torque is occurred at what slip. This data can be calculated by constructing the circle diagram. So this problem is based on no-load test data. So in a no-load test, three-phase induction motor took 10 ampere and 450 with a line voltage of 110 volts. If stator resistance is 0.05 ohms per phase, and friction and windage losses are given here. Friction and windage loss 135 watts. Calculate the exciting conductance and susceptance. Conductance means G0, which is reciprocal of R0. From no-load test data, we have only calculated R0 and X0. This is B0. But this is a different problem he has asked. Generally, we are calculating R0 and X0, but he is asking reciprocal of that values, G0 and B0. Just note down the problem. No-load test data. What is the given data? It took 10 amperes. The no load current is given as 10 amperes. The input power is 450 watt with applied voltage of 110 volts. Right. So given data. I not given as 10 amperes. Power input 450 watts and applied voltage and friction and windage loss 135. Stator resistance 0.05. Ohm per phase. Friction and windage loss 135 watts. Then calculate exciting conductance and susceptance. We know that from no load test, this is the applied voltage. And what are the no load parameters? You can also represent. This is the no load current, I naught. V naught is the applied voltage. Now this in terms of G naught, B naught, R1, J, X1. This is the no load parameter. So where G naught is 1 by R naught and B naught is, can calculate reciprocal of reactance. And if you know admittance, you can find out. You can find out B naught. B naught equal to square root of Y naught square minus G naught square. As we know already, you can find out. If you know R naught, if you know Z naught, you can find out X naught. X naught equal to square root of Z naught square minus R naught square. Same way, in this way we can find out B naught. Already this is given as 110. If we consider for phase 110 by root 3, I naught is given as 10 amperes, R1 is 0.05. Then find out G naught. G naught, to find out G naught, first of all, what is the power he has given? Input power is 450, friction and windage loss. Then what are the copper loss? Stator copper loss. How to calculate stator copper loss? The stator copper loss I naught square into R1. Since stator resistance is R1, so we can find out I naught R1, but for 3 phases we have to find out 3 times. So what is I naught? 3 into 100 whole square. R1 value is given as 0.05. this is going to be 3 into 10 square into 0.05, 15 watts. But friction and windage loss 135. Then what is the input power? Already given as 450 watts. Then what are the core loss? Core loss is nothing but W naught, which is equal to input minus what are the other losses? Windage and friction. So what is the windage? Input power is 450 minus windage and frictional losses are combiningly 135 plus one more loss is there, that is stator core loss. Already we have calculated. What is the stator core loss? 15. So minus stator copper loss. Right. So 450 minus 135 plus 15, 150. So 300. 300 watts is the core loss component. So by knowing this core loss component, you can find out what is R naught. We know that 3 I naught square R naught is equal to core loss. And what is R naught? What is W naught? 300 by 3 into 100 whole square. So 300 by 300 by 100. How much? 0. This is R naught, but we want reciprocal of this. So therefore G naught will be 0.04. Sorry, R naught will be 0.04, but we want only G naught. G naught is reciprocal of R naught, which is nothing but much you are going to get this value 3, reciprocal of this value 0.025. For R naught, the units are resistance per phase. But what about G naught? Reciprocal of ohms, that is Siemens for phase. Siemens for phase. This is G naught. Similarly, we can find out G naught, sorry, Y naught and B naught. Right. To find out Y naught, we know that relation between V and I, V equal to IZ. The same fashion, what is I? Y is nothing but reciprocal of Z. So we can replace V naught with I by Y. So therefore, Y naught is equal to I naught by V naught. So therefore, I naught is 100, V naught per phase voltage 110 by root 3. is going to be Y naught. How much? Just calculate and tell. 0.158. Here in the problem, he has given I naught is 10 only. So 10 years, only 10. Just make a correction. I naught is given as only 10 here, not 100. So 10, this will be okay. Right. Here also 10. Right. Right. Now calculate. So Y naught will be 0.158. This is Y naught. So if you know Y naught and G naught, we can calculate B naught by using, earlier we have discussed this formula. B naught equal to square root of Y naught square minus G naught square. Minus G naught square. To substitute here, Y naught is 0.158 whole square minus V naught 0.025 whole square, and simplify, you are going to get B naught value as how much? 0.156. B naught will be 0.156. The units for this is also Siemens per phase, right? So here only is asking susceptance and conductance, not resistance and reactance. So in this way we can do this problem. Next, power flow diagram and efficiency. Power flow, what are the various powers occurred in the three-phase induction motor, and what are the various losses. We are giving three-phase AC supply to the stator, right? And we are going to get output, and this is the input three-phase AC supply. So what is the input power? Root 3 VI cos pi. And what are the core losses? Core losses is nothing but hysteresis and windage loss, hysteresis and eddy current losses, stator core loss. Then after deducting this, directly the input power minus stator core loss is nothing but power input to the rotor. So this is nothing but air gap power, that is input to the rotor. So in the rotor there will be rotor windings, three-phase rotor windings, and what is the loss occurred in the three-phase windings? I square R, that is 3 into I square R, that is known as copper loss. These are the rotor copper losses. Rotor input minus rotor copper loss is nothing but mechanical output power. This is the mechanical power, and after getting mechanical power, if there is any losses, that is nothing but friction and windage loss. Whenever there is a rotational, there will be friction and windage. So by deducting friction and windage loss from the mechanical losses, from mechanical input, we are going to get shaft output. This is the shaft output. So finally, what is the efficiency of this induction motor? Output by, what is the output? Mechanical output or shaft output by electrical input power. Or if you are neglecting friction and windage loss, P mechanical by P input power. Explain the starting methods of three-phase induction motor. So in the university exams, the very, very important question that was asked is, explain the starting methods of three-phase induction motors. So generally, in order to start any machine, why to start with the help of starters or any starting methods? Right. If you take DC motors, for DC motors, without starters, how can you start the DC motor? So generally, in case of DC motor, the armature current will be given by V minus EB by RA, where RA is the armature resistance, V is the applied voltage, back EMF produced in the rotor is EB. So when at the time of starting, EB is 0, just we are about to start the motor, just we are applying the rated voltage here, but at the time of starting EB is 0. Whenever EB is 0, then the starting current will be VA by RA. VA is the applied voltage. Full voltage we are applying, 220 volts we are applying, whereas armature resistance is 0.5. So such that what is the current we are going to get here? Approximately 440 amperes. So very dangerously high current is we are going to get from this. So if you are applying direct voltage here, the starting current is very high. So in order to avoid the starting current, huge amount of starting current, normally we are using starters. So in case of DC motors, we are using 3-point starters. Whereas in case of induction motor, three-phase induction motors, how to start induction motor? Is it necessary for three-phase induction motors also? So starters, without starter, what happens? The starting current will be 5 to 7 times of full load current. So in this case also, in three-phase induction machines also, the starting current will be flowing 5 to 7 times of full load current. So whenever the rotor is at stationary, and the rotor is stationary means slip is ns minus n by ns. When the rotor is stationary, that is n equal to 0. When n equal to 0, slip will be 1. That is the standstill condition. When S is 1, what is the starting current and torque? You know the torque is directly proportional to E2 square S R2 by R2 square plus SX2 square. When S is 1 and it is inversely proportional to rotor resistance. So by changing the rotor resistance, we can control the speed or torque. So here the starting current will be very high in case of three-phase induction motors also. So what are the starting methods for squirrel cage induction motor? If you are applying full voltage starting method and if you are applying reduced voltage method, and as we have seen, the torque is directly related with E2 square. E2 square is the applied voltage, square of the applied voltage. So as the voltage increases, the torque increases. As the torque increases, speed of the motor increases. So if you are applying full voltage, this is known as full voltage starting method. If you are reducing the voltage, there will be certain techniques for reduce the voltage. So starting torque will be very high when we are applying full voltage starting method. If we are applying full voltage means the winding will get heated up. Within a short period of time we are applying a huge amount of voltage. That's why the windings has to be designed in such a manner that it can retain the huge amount of starting current. So full voltage starting method means this is also known as direct online starting method. We can use DOL starters. We can find DOL, direct online starters, in agriculture fields and also in the household purpose. To get the water from the sump, we can use these direct online starters only. So in this method, what is the current? So current will be 5 to 7 times the full load current. So the amount of current drawn by the motor depends upon its design size. But high value of current does not harm the motor because of rugged construction of the squirrel cage induction motor. We have already discussed in the last session the induction motor construction. It is designed with 3-phase windings with the rugged construction and robust. It can be used anywhere, means under any contaminated areas also we can use, underwater, underground, in any coal mines also we can use the induction motor. So that's why this type of induction motor can also withstand the direct supply high voltage. Next, reduced voltage method of starting. So for squirrel cage induction motor, we can reduce the voltage by using 3 different ways. The first one is stator resistance starting method. Stator resistor starting method. Here we are using variable resistors, or we can also use variable reactance also. And auto transformer starting method. Next one is star delta starting method. So direct online starting method is applicable only up to 5 HP. We can use only up to 5 HP motors, we can use direct DOL starter method. So beyond 5 HP, that up to 10 HP we can use this stator resistance starting method. Auto transformer up to 20 HP, and beyond 20 HP we can use star delta starting method. So this is the diagram for variable resistor or reactor starting method. Here the applied voltage is √3, that is the phase voltage. Right, here this is the applied voltage. We are giving by means of a 3-phase variac. 3-phase supply is taken here. Full voltage we are going to get here, and by this the adjustable voltage can be obtained by using variable rheostats or reactances. So we can use either resistor or reactor. So this is the reactor. If you are using resistor means this diagram will be like this. So what percentage of reactance or resistance is obtained is X. So √3 X V1. So then what is the phase voltage here we are going to get? V phase is equal to √3 X V1 by Z phase. So here X amount of fraction we are going to get in the current. So therefore the starting current will be, starting current in this method will be, the variable factor is X times the full load or short circuit current. So short circuit current, phase current means short circuit current we can take. So IST is equal to x times of IXC. Then what about the starting torque and full load torque? What is the starting torque? The ratio of starting torque to full load torque is given by the relation IST by IFL whole square into SFL. How this formula came? Already we have derived the expression for starting torque and full load torque. So from that, take the ratio, or else we know that torque is directly proportional to I2 square R2 by S. So torque is directly proportional to I2 square by S. By using this relation, also we can get. So here for starting torque, TST equal to rotor current IST square by, for starting slip is 1, for full load IST whole square by IFL. This expression can be rewritten like this. For starting torque, IST square by 1, and for full load, IFL full load current by full load slip. If we take the ratio of these two, we are going to get this expression. Right. So now, what is the starting current by using this stator resistance and reacting starting method? The starting current is X times of ISC. If we resubstitute in this, we are going to get starting current is equal to, or starting current to full load torque. Starting torque to full load torque is equal to IST we can replace with X. So IST by ITFL, TST by TFL is equal to, IST is nothing but X times of IXC, X times of ISC by IFL whole square into SFL, right? So this is the formula for starting torque to full load torque in case of stator resistance or reacting starting method. Similarly, the next method is auto transformer method. So what is the difference between this method and this method? Here we are using manual way of variable rheostat or resistors. Here this is auto transformer. So the speed control is very smooth by using auto transformer method. So here the supply voltage as well as current both will be changing by a factor of X here. Earlier case we have seen only current is reduced. Here both voltage as well as current will be changed in terms of X factor. So therefore the input power or the applied voltage into current will be P is equal to root 3 X times of V1 into current X times of ISC. V1 ISC. Then what is the starting current? Here the starting current is, again, what is the starting current here? Starting current is nothing but X times of ISC. X times of ISC. Then what is the ratio of starting torque to full load torque, the ratio is given by same formula, IST by IFL whole square into SFL. So which is equal to x square times of ISC square by IFL whole square into SFL. Next, star delta starting method. So while starting the induction motor, first of all it is connected at the time of starting, the stator winding is connected to the start delta connection, star connection. While starting it is connected to star, and during running condition it is connected to delta. So both the starters are used here, star delta starter. At the time of starting you have to connect to a star network or star circuit. During running condition the switch has to move to running condition or delta connection. So here both the connections are used, star and delta. At the time of starting it has to start with star connection. During running, once the running speed occurs, then the switch has to move to delta connection. So while changing star to delta, how the current is transformed? The starting current during starting will be V phase by Z phase root 3 times. So V phase by I phase is short circuit current by root 3. This is the starting current in case of star. For star, if it is delta, during running condition the starting current will be equal to root 3 times of V phase by Z phase, root 3 ISC. So if you take the ratio of starting current in star to starting current in delta, it will be equal to ISC by root 3 into root 3 into ISC. So the ratio of starting currents in star and delta is given by 1 by root 3. So similarly, you can find out the ratio of starting current to full load torque. Which is equal to IST by IFL whole square into SFL, which is equal to TST. During starting, what is the current? ISC by root 3. So 1 by 3 times of ISC square by IFL square into SFL. So starting current will be reduced by 1 by 3 times of full load torque. Starting torque will be reduced by 1 by 3 times of full load torque. So we can do this problem based upon same application star delta starter. So due to less time we cannot solve this. So we can solve based upon by applying the same formulas here. So he is asking star delta starter. So you have to apply this formula. Starting current will be equal to 1 by 3 times of starting current in delta. So starting torque to full load torque, use this formula, you can solve this problem. Then let us go for describe the different methods by which speed control of induction motor is achieved that is control from stator side as well as rotor side. So we can control the speed of the induction motor both the way, that is either by stator control method or by rotor control method. So what are the stator control methods? So stator control methods are nothing but so we know that speed of the motor is ns into 1 minus s, where ns is 120 f by p. To control the speed, what are the parameters involved here? Frequency and number of poles and slip. And frequency again depends on supply voltage. Based upon the supply voltage, the frequency attains. So what are the parameters? Supply voltage, supply frequency, number of poles and slip. These are the factors. By changing these factors, the speed of the motor will changes. Speed control by changing the supply frequency. So frequency is directly related with speed. As frequency increases, speed of the machine will increases. Then supply voltage. Already we have seen the torque expression. By changing the applied voltage, your torque expression is nothing but torque is directly proportional to square of the voltage. So torque is directly proportional to E2 square of the voltage. So if the applied voltage increases, naturally starting torque increases. So for small change in the applied voltage, the torque will be changes with very high amount. Then pole changing schemes. So we know that ns is equal to 120 f by p by changing the number of poles. But physically there will not be any poles in the induction motor. But based upon the windings that we have designed to the stator and rotor. So if the stator is designed with certain manner, same whatever amount of the poles formed in the stator, same amount of poles will be formed in the rotor also. So based upon the winding design, the number of poles will depends. Then rotor resistance control. This rotor resistance control can be applied only for slip ring induction motors, where in case of slip ring induction motor, the slip rings are placed like this. If this is the stator, then rotor is always designed in the form of star, and these each windings are connected by means of a slip rings, and to these slip rings variable resistors are connected. For each phase, variable resistors are connected like this. So this is stator and this is rotor. So by varying the rotor resistance here, we know that torque is inversely proportional to rotor resistance by the torque expression, right? So torque is inversely proportional to rotor resistance. As rotor resistance increases, torque will decreases. As rotor resistance increases, slip is nothing but R2 by X2. Rotor resistance increases, slip increases. As slip increases, the relation is ns 1 minus s. As slip increases, speed decreases. So as slip increases, rotor resistance increases, torque decreases. Slip increases, speed decreases. So both torque and speed are directly related. So by changing the rotor resistance, we can control the speed of the motor. a cascade connection. So two different machines can be coupled. So two different machines means we can connect one squirrel cage induction motor coupled with slip ring induction motor. Slip ring induction motor. So these two are coupled here. So there will be these slip rings. With the help of slip rings, we can connect like this. Now, let us assume the number of poles here it is PA, number of poles is PB, and we are giving supply here, input supply, and these two rotors are coupled here. Then what is the net speed of the machine? The net speed is given by 120 F by, if the rotating flux in the stator in both the cases are in the same direction, then it is called as cumulative way of connection. Then in that case, the speed will be 120 F by PA plus PB. But other way is, for differential mode of connection, the rotating flux in this first machine is different from second machine. Then this is called as differential way of connection. Then the speed will be PA minus PB. So in this way we can cascade the two different machines. This is the problem based upon what must be the rotor resistance to be added to get the speed adjusted to lower value. Already it is running with certain speed, and what must be the resistance to be added to get the reduced speed. This is the example for speed control method. Then finally, induction generator. So till now we have discussed with induction motor. Then what is generator? What is the difference between motor and generator? As we have seen for DC machines, DC motor and generator, physically there will not be any difference between DC motor and generator. By the operation only we can differentiate DC motor and DC generator. The same manner, induction machine is a single one which can be act as both motor as well as generator. So physically there is no difference between three-phase induction motor and three-phase induction generator. So based upon the operation, when the speed is less than synchronous speed, then the machine will access induction motor. When the speed is greater than the synchronous speed, then slip will be negative. So in this case, the machine will access induction generator. Here, induction motor. If speed is equal to ns, neither it will access motor nor generator. So here, induction generator, while operating induction generator, the condition should satisfy is the speed of the machine will be greater than the synchronous speed. Means the rotor of the machine has to be rotated by some external prime movers such that the speed should be greater than the synchronous speed. Whenever speed is greater than synchronous speed, slip will be negative. Negative slip indicates slowly the rotor speed decreases, finally becomes zero and starts rotating in the reverse direction. Reverse direction means from the supply goes to load to source. Now the stator windings will act as a stator, it will produces the EMF. So EMF will be induced in the stator windings. So that's why here the rotor is transferring the power from mechanical to electrical. So that's why it is acting as a generator. So what is the advantage with induction generator is it can supplies the leading power factor. So this is the circuit diagram. This is the prime mover coupled with induction generator. So if you are rotating prime mover, the rotor of the generator will rotate and EMF will be induced in the stator windings, then electrical power goes out. So it will supply the leading power factor and draws the lagging power factor. So within this time I covered, I think covered so much data. So it may be very useful to you for, to do success in the examinations. So if you have any doubts, please mail or chat with me, and please subscribe and share. Thank you for watching ACE Engineering College YouTube live session. Thank you.